So good afternoon, everyone. Thank you very much for being here today. My name is Mohammed Al-Sakhawi, and today I'll be talking about DPDK and how to use it to make your Neutron deployment faster. Before I do that, I'll just give you an idea of where I work and what we do. I work for SharkNet, which is a multi-university consortium here in Canada for high-performance computing. We operate the Gram supercomputer, which is one of the top 3 supercomputers here in Canada, with around 2.6 petaflops of computing capacity. I'm also the operational lead for the National Cloud Team for Compute Canada, which is in charge of cloud operations across Canada. We have 4 major OpenStack deployments, around 10,000 physical cores, and around 2 petabytes of Ceph. So before I go ahead with the presentation, I actually wanted to ask the further question, do VMs need to communicate faster? Because it wouldn't make sense to go through a presentation of improving network performance for VMs if they actually are performing adequately right now. The answer for this question is going to always be yes. VMs need to communicate faster, and because of the changing paradigms of application in the cloud. Cloud applications traditionally have been application servers, database servers, and web servers, and those are all kind of applications that can fit within the existing layout for the network in the cloud. However, more and more applications are joining now the cloud club, such as NFV or HPC or real-time applications, and all of these kind of applications require very low latency and very high throughput. So the traditional layout of network in the cloud has to be readjusted or revisited to actually fit the requirements for the network for those kind of applications. So in order to look on exactly how to make this possible in the cloud, how to achieve lower latency and higher throughput, we first need to look at what exactly makes Neutron fast. The first thing to remember here is that Neutron servers are only used for virtual network provisioning and not for packet flow. So when you look at Neutron server, L3 agent, ML2 agent, all of these kind of agents or the service themselves, they only allow you to provision your infrastructure. They don't actually have packets flowing through them. The packets actually flow through the virtual network, so your Open vSwitch, your tab device, your vEth pair, and so on, and that's what will affect the performance of your communication between the VMs. We can summarize the factors affecting the latency and throughput between VMs in an OpenStack environment to 3 main factors. First is how fast does the VM produce or consume traffic, and this is basically something internal to the VM itself. In other words, how fast does the VM produce enough packets to throw them in the pipe to be sent out. A second is how fast does the virtual NIC emulation happen, and how fast the transport of those packets are moved over the next step, which is a virtual network. And lastly is how fast is the virtual network components operating, such as your Open vSwitch, your vEth pair devices, as well as the physical NIC itself, because you're still using the physical NIC even though all your network is virtual. So in this presentation, first we'll be looking at some background concepts which will help us understand the components of VM's traffic flow. We'll then look at traditional layout of VM's network on OpenStack. So once you deploy an OpenStack environment and you have your compute hosts running, how does the VM send traffic out, and where are the components that actually the packets pass through? We'll then identify a problem with this current layout. So what exactly is the bottleneck and why is it there? And then we'll look at DPDK as an enabler for faster packet processing in Linux. We'll then look at OVS DPDK as the enabler for that in OpenStack. So basically, this is what your VMs will communicate with or will send traffic to. And lastly, we will look at the DPDK-enabled layout of VM's network in OpenStack. The concepts I want to talk about first are 3 concepts. The first one is virtual NIC emulation and transport, and second one is OVS Datapath, and lastly is the NIC transmission and receive process. So the first concept is basically virtual NIC emulation and transport. We're all accustomed to this diagram. Basically, VM has a virtual NIC card inside of it. If you want to send traffic, you will send the virtual NIC. It will end up on a tab device on the host. But how is it physically implemented? The answer is VirtIO. So VirtIO is a standard for para-virtualization device emulation. It basically defines how can you emulate devices in a virtual environment. And VirtIO is divided into 2 main portions. The first portion is VirtIO front-end, which is what your VM will actually deal with. It's a driver sitting inside your guest VM. And there is a VirtIO backend outside of the boundaries of your VM. And it's either implemented inside KeyEMU, the hypervisor itself, or inside the kernel. The KeyEMU hypervisor implementation looks more like that. You basically have your guest running in the user space. You have the VirtIO driver inside of it. It will send traffic to that. The VM will send traffic to this one. It will be handed over to the KeyEMU process to continue the emulation. So basically, a VirtIO backend within the KeyEMU process itself. KeyEMU will do the actual emulation at the host level, so it will do system calls to the actual kernel stack, and will then inject the traffic into a tab device in the kernel stack. This definitely has a problem that your KeyEMU process is now a bottleneck in every traffic that gets sent out of your VM. So there's different approach for having VirtIO backend, which is the kernel VirtIO backend. And this basically relies on what's named as vhost-net, which is a kernel module living in the kernel space. You will send traffic this time instead of the user space process to actually a kernel module in the kernel space. which looks more like that. Basically, you have your guest generating traffic, throwing the traffic over on VirtIO driver in the user space. Then this traffic will be handed over to a vHostNet module in the kernel space. Obviously, this is a better approach because you're trying to move away from having a user space process as your intermediate for every packet that you send out. Still, the injection to tab device still happens at this case, and then the traffic will flow through the network stack of the host, or depending on the virtual switching that you have for this VM. In order for you to tell if you're using that or not in your deployment, you could easily do that by doing ps-ef and grabbing VirtIO net on one of the compute hosts, and then looking for the net def definition. So basically the network device definitions. If you find vhost equals on, then basically you're using the vhost backend for VirtIO. The second concept I want to talk about is OVS Datapath. So we're all accustomed to this diagram. Basically, port 1, port 2, and port 3 are part of a virtual switch. And you send traffic between the ports depending on the flow rules of the switch itself. But how does the traffic actually flow? The key word here is the kernel data path. OVS provides a kernel module, a lightweight kernel module in the kernel space, which allows your traffic to flow between the ports. And the module's name is OpenVSwitch module. And the layout of the deployment for OpenVSwitch looks more like that. You have your OVS DB server, which is user space process living in the user space, storing the configuration for your switch. Then you have your OVS vSwitchD, which is a user space process you use to deploy your switch. And then you have the forwarding plane, or the kernel module that I was just speaking about, and that's where all the flowing of the packets happen. So basically, the packets will flow between the ports in this kernel module you guys see here. When the kernel space module receives the traffic, it doesn't know what to do with it. It will have to use the netlink protocol to execute what's named as an upcall to the actual user space process, OVS vSwitchD, to ask it, what should I do with this packet? OVS vSwitchD has better visibility on the flow rules for the switch, so we'll actually decide what to do with the packet and send it over back to the forwarding plane to execute on that. You can see that using the command line by using OVS appctl dpctl show. So basically, it will show you the data path that you have in your system. The one we have here is system at OVS system. The first portion you see here before the @ sign is the type of the data path. So when you see system, this is basically an acronym for the kernel space data path for OpenVSwitch. And as you see here, I'm doing ls-mod and grabbing for OpenVSwitch. So I'm looking what modules are loaded on the host. An OpenVSwitch module is loaded on the host, and that's basically what's doing my forwarding for the traffic. Obviously, if I kill this module using rm-mod or force that, I'll lose all the traffic between the VMs or between the ports in the switch. Last concept I want to talk about before going ahead with the core of the presentation is the NIC transmission and receive process. Because even with the best virtual network, your packets still have to end up hitting the actual NIC at some point. So the core component in Linux that's responsible for sending and receiving traffic, as well as configuring the NIC, is the NIC drivers. Those are usually kernel space objects. This is the kernel space. And you can see from this diagram, basically, a NIC attached to the kernel space. From there, or attached to the host, which basically causes the creation of memory structures in the kernel space to support this NIC. Those memory structures are Rx and Tx descriptor rings, you see in here, which are basically ring-like structures that point to where packets will be sent or received. So the packets that you will send will basically have pointers to them in the Tx descriptor ring, and the packets that you receive will actually have pointers to them in the Rx descriptor ring. But those are not actual packet contents. They are just the descriptors for the packets or pointers to the packets. The actual packet contents will be in the packet buffers in there, which are basically DMA-able memory region in the kernel space. This allows the NIC to directly copy packets over from the NIC itself or the actual hardware on the NIC to memory in the kernel space without hitting the CPU in this case. When the NIC receives a packet, what will happen first? The NIC will try to fetch an Rx descriptor. So basically, we'll look, do I have enough descriptors to receive this packet or not? If it can do this, it will then DMA the packet contents into the packet buffers. DMA means that we're not using the CPU for copying. It's basically using the DMA engine on the NIC itself for writing. And then it will initiate an Rx interrupt. So basically, it will have to raise its hand to the operating system, tell it, I have received the packet, come and service it. This will, the interrupt, when it gets serviced, it will execute the interrupt handler for the driver of the NIC, which will then first disable further interrupts on the NIC, and then add the NIC to what's named as a pull list. The pull list is basically a list of devices who have packets or of traffic that needs to be harvested, in this case. When the pull list, you have it, the device in it, then a soft IRQ is initiated, or a soft interrupt is basically initiated, which when serviced will actually do the actual harvesting of the packets from the NIC itself. The harvesting happens using a pull statement, which basically looks at the Rx descriptor ring and then gets the packets out of the packet buffers and pushes them up the network stack. Once this is finished, interrupts are re-enabled on the NIC itself to allow more interrupt-based or interrupt-driven packets to be received. So we can look at traditional layout of VM's network OpenStack based on those concepts to be looking like that. We have a VM here, which has a virtual NIC card inside of it. You send traffic, it goes to a tab device. A tab device is where your security group rules are applied. Then it's attached to a QBR, which is the Linux bridge. Out of that, there's a QVB and QVO, which is a VETH pair, basically a virtual wire. Out of that is the integration bridge, the tunneling bridge, and the physical NIC. Integration and the tunneling bridge are basically OVS switches. This is a conceptual layout, so basically this is what you write from a logical perspective, but how is it physically implemented? It actually looks more like that. You have your guest running in the user space. It's basically a running process, a regular user space process, has a VirtIO driver inside of it. You send the traffic, it gets handed over to the vHostNet kernel module in the kernel space. Out of that, it gets injected into the tab device, which is implemented using the TUN module. And then the IP tables rules have to be applied, and that's where the network stack NIT filter has to be involved. Then your tab device also is connected to a QBR Linux bridge, and that's where the bridging module has to be involved as well. Out of that, you reach the VETH pair, which is QVB and QVO, and that's where the VETH module is involved. And out of that, you reach the integration and tunneling bridges, which are an OVS forwarding plane. If the traffic needs to leave the host, then it involves the NIC driver to actually leave the host on the NIC. Obviously, this is a big diagram. There's lots of components in it, but that's basically the core of the problem that we're having with OVS right now, connecting VMs to it. The problem is that there's lots of components, as you could see in this diagram. We'd rather have a smaller component diagram than a bigger component diagram to achieve better performance when it comes to latency and throughput. So the main problem, as you see here, the packets are generated in the user space and they're sent to kernel space. And once they join the kernel space, there's lots of components that you actually have to follow through. They start incurring too much overhead in there. And other thing is that the Linux network stack has to be involved, basically for net filter rules, for sending the traffic out. And this means that you have to represent the packet in a way that the Linux network stack understands, which is the very famous SK buffer or socket buffers. Socket buffer is very well known to be a large struct, has lots of metadata in it to support as many protocols as possible. So it's mostly compliant with many protocols. But this is not doesn't fly well with any kind of high performance networking. Because basically, if you're doing high performance networking, you want small structs to be able to process them fast. There's also the allocation of those SK buffers. Basically, they have to happen on every packet that you send out. So you allocate memory for the packet, you send it out, and then you allocate that. This is very expensive from a CPU point of view. You also have the interrupt-driven sending and receiving. So the receiving only happens once the NIC will raise its hand to the operating system and tell it, I received the new packet, come and process it. In other words, the operating system will never know that there is a new packet unless the interrupt gets serviced in this case. Although any API tries to change that temporarily from interrupt-driven to polling I/O, which is what I mentioned earlier about disabling interrupts and then re-enabling interrupts at the end of the polling statement. But it's still, the actual I/O is done through interrupt-driven approach. And this diagram here I have is not even conclusive. There is lots of components I don't have in it, just for simplicity and because there is lots of individual modules within every individual component. If you want to know exactly what gets executed when you send the traffic from one of your VMs to the outside world, you can easily look at System Tab. It allows you to put tabs or probes in the kernel, and you can actually see what happens or what gets executed when you send a single packet from your VM to the outside world. And you'll be amazed how many functions have to be executed and how many modules have to be invoked for every single packet that gets sent out. This problem even becomes more bad because it has to happen every single packet that you send out from your VM. So very fast, you will notice that there is a minimum latency that you can't achieve anything lower for your VMs. So basically, the minimum latency is capped. You have this much overhead, and you can get any way below it because you can't get rid of this overhead. This overhead is basically used for kernel processing. There's also a problem with throughput because if you use small MTU for your packets, basically you have to generate more and more packets to fill the pipe. But more packets mean more overhead processing, which means more overhead cycles or more CPU cycles. But your CPU can only provide a limited set of cycles for you to process. So at the end of the day, you will reach a certain limit when it comes to throughput as well. And that's basically where DPDK comes in. DPDK tries to resolve those issues by providing a way to remove this overhead processing from the entire picture. DPDK is a set of libraries that enable faster packet processing in a Linux environment. And they do that by replacing or bypassing the Linux network stack altogether. So they basically make sure that your packet does not flow through the existing architecture for network for Linux. It also operates entirely in user space. So basically, the packets do not have to traverse the boundary between the kernel space and the user space just to be sent out. One thing I mentioned here is there is no escape buffer. And this is something that you get out of not using the Linux network stack, is that you don't have to represent the packets in a way that it understands, because now you can represent it in a more meaningful way for higher performance processing for the packets. DPDK has multiple components in it. The first component is EAL, which is Environment Abstraction Layer. This is basically an abstraction layer for hardware and memory. So basically, it allows you to deal with the hardware and memory without giving low-level calls to them. It allows you to initialize the memory structures that you give for DPDK as well. Second thing is a set of libraries that allow you to represent packets, represent buffers, represent rings as well, because those are basically stuff that has already been implemented in the Linux network stack. But since you're giving away on it or giving up on it, you have to be able to represent the packets in the same way, but in user space this time. So there is a mempool library, mbuff library, and ring library, which I'll explain most of these in the coming slides. And last thing is the poll mode drivers. So polling mode is sort of the contrast of interrupt-based mode or interrupt mode. Polling mode is continuously sending or receiving traffic without waiting for an interrupt to drive this sending and receiving. So DPDK relies on poll mode drivers, which basically live in the user space, to continuously send packets in and out of your environment. What makes DPDK fast? First, that everything happens in user space. Your application, your DPDK stack, and the NIC itself happen in user space. So there's no kernel overhead for sending the packets out or receiving them. Second thing is there's custom memory management. As I mentioned, we're not using the Linux network stack, so we don't have to represent the packets in any way that the Linux network stack represents it. So basically, we can be very geared or tailored towards higher performance processing. There's custom structs, RTMBuff, which is basically a message buffer struct. It is specific for DPDK, and it's used to represent packets. You also have buffers that are allocated by user space applications while starting, so there is no allocation on the fly. There is actually the packets or the packet buffers are allocated before the application starts. This way, you don't have to pay the expense from a CPU cycle perspective for allocating the buffers and then deallocating them. Huge pages are also used to avoid any kind of TLB misses. Tries to reduce them, not entirely avoid, I would say, in this case. There's also polling for sending and receiving traffic. So as I mentioned, interrupt-based I/O means you have to actually raise your hand to tell the operating system, I have received the packet, or basically nudge the operating system to tell him, send this packet out. It's a bit different in this case because your driver will be continuously working on a dedicated core. So PMDs run on their own dedicated cores to send the traffic in and out of your environment. One thing to mention here is this might be a bit disadvantage for people with very small OpenStack deployments or very large OpenStack deployments, because there's sort of a tax in here that you have to pay, which is the number of dedicated cores you have to give to your PMDs. Normally, you can give one per your NUMA cell. So if you have, let's say, 10 cores per socket, you're basically paying a 10% tax for having this network performance. So if you have a very large deployment, you're actually paying 10% of your cores for just non-general purpose computing, just for your network to operate. So OVS with DPDK is basically the enabler. It allows you to connect your VMs to, in an OpenStack environment to DPDK and basically utilize it. And as you can see, this is a diagram for it. There is no kernel data path in this case. So the user space is basically the largest portion of it, but there is no kernel space altogether. The main feature of it is that the user space data path, so the data path itself exists in user space. And the keyword for that is usually netdev, or the name. As I mentioned, there's a type of data path as an OVS. The most common one, or the default one, is called system, which is the data path in the kernel space. And there's another one, which is the user space, called netdev in this case. Your virtual ports will exist in the user space. Your NIC will exist in the user space. And the sending and receiving will happen still in the user space. So from this diagram, you see that OVS DB server, you can see that OVS DB server still exists. OVS DB server will still contain your configuration for your switch, and nothing will change about that. Your OVS vSwitchD will actually be a bit more expanded. You see there is more threads within it, such as the PMDs in here, which are continuously working or accessing the NIC through what's named as VFIO PCI. I'll explain these as well in the coming slides. But basically, they don't wait for interrupts from the NIC. They work in the user space, and they check the NIC. Has anything arrived? If it does, then you process it right away. As you can see here also, there is no connection between the QEMU process or the guest VM in the user space and the current space altogether. So there is no use of vHostNet in this case. There is a VirtIO backend that exists within OVS itself, which is named vhost-user. You can see this, as I mentioned, using command line by using OVS appctl dpctl show. And you see here that it's using netdev at OVS netdev. So netdev is basically the keyword for user space data path for OVS. In order for OVS to be able to move everything to user space, it has to achieve 4 main tasks, in collaboration with DPDK for sure. First, it has to be able to move the NIC to user space such that it can actually access the onboard registers, configure the NIC in user space. It has to be able to provide memory for transmission and receiving in user space. It has to be able to provide drivers for sending and receiving in user space. And it has to be able to provide VirtIO backend or VirtIO handling in user space. In the coming slides, I'll be explaining each one of these in details of exactly how everything is shuffled from the kernel space to the user space. So moving the NIC to user space, as I mentioned, DPDK likes to run in the user space. So there is a need actually to move the memory structures that exist here in the kernel space, which are basically structs created by the kernel driver itself, to the user space in this case. And since DPDK runs in the user space, it basically have to give up on those kernel level structs. So DPDK will give up actually on the kernel driver altogether. So when using a NIC with DPDK, you will have to give up on using your normal traditional driver for the NIC in the kernel space. You will use a different kind of driver. It's PCI or path-through style driver, which will allow you to access the NIC in user space and do 3 main functions. You'll have to enable you to access onboard registers for the NIC, basically in user space. It has to be able to handle the interrupts in the user space. And it has to allow you to allocate memory for the NIC to DMA from or to a user space. The pass-through style driver of choice for DPDK is VFIO, and utilizing what's named as IOMMU for isolation and address translation. VFIO is a pass-through style driver, as I mentioned. So the idea about pass-through style drivers is that they don't actually provide you structs in the kernel space. They allow you to reach the device completely in the user space itself. So it allows you to create memory structures to DMA from and to for the NIC in user space. It allows you also to have direct access to the NIC registers in user space, so basically to be able to configure the NIC in user space, and to move the ownership of the NIC from a kernel driver to actual user space process. There is always an implication of having any kind of DMA-capable device, that there is always a possibility of DMA attacks, which means that the device will access memory outside of its boundaries. So this becomes even worse providing the NIC to a user space process, because this means that the user space process basically controls the NIC and can ask it to do whatever it does with the memory of the system. And that's where IOMMU comes in place. IOMMU is Input-Output Memory Management Unit. It's a physical chipset in your motherboard, which basically provides isolation and address translation. It makes sure that if the NIC is requesting access to a certain memory, it can do this. It has the rights or privilege to do that. It also makes sure that whenever a NIC is accessing a certain memory, it does not do that with physical addresses. It does that with what's named as IOVA, or Input-Output Virtual Addresses. So it basically does the translation for that. Once the NIC is bound to a VFIO, it's now become a DPDK-compatible NIC, or basically a DPDK interface. In order to achieve this from a command line perspective in your Linux environment, you can use a utility that comes with DPDK. It's called DPDK-bind, which basically allows you to bind any device that you have in your system, network device in your system, to VFIO. I'm using here DPDK-bind-s, which basically to show me the summary of what I have in my system. As you can see here, it's showing me that those are the network devices using the DPDK-compatible driver, and there is none. There isn't any of them. There's also network devices using the kernel driver, which is basically the default that you will have by attaching a NIC to your system. And this is what causes the allocation of memory spaces in the kernel space for the driver, for the device to operate. I'll pick up on the first one, which is this one you see in here. This is the address, PCI address for it. And it's an Intel 10 gig NIC. It's using the IXGBE driver you see in here. And I'd like to move it to user space by providing VFIO binding to it. So I'll use a command line again for DPDK-bind -b, and then specify the driver that I will use, and then the address for the NIC itself. So as you could see here, the NIC has been moved from the kernel driver to a DPDK-compatible driver. So in this case, now the NIC is in user space. I can actually reach and basically handle the NIC in user space. And this mentioning here, it's using the VFIO driver, and it's unused IXGBE. So basically, it is not using the kernel driver anymore. Once you have the NIC in user space, now you have to instruct OVS to start using it. In order to ask OVS to start using it, you have basically to create a new bridge. Now I'm creating BR5 in here, and I'm adding a new port to it. The port, as you can see, its code name is DPDK0, and I'm providing it with what's named as DPDK dev argus, and then the address of the NIC that I just moved to VFIO PCI. So I'm creating a new port. It's called DPDK0, and the type is DPDK. This is a bit different from adding a regular interface using ETH2 or ETH1 way we're used to having kernel drivers, because moving away from a kernel driver means that you actually are giving up on all those structures that came with it. So you don't have a handle to deal with the NIC in the user space using ETH2 or EM or whatever kind of letters get assigned to your NIC to operate. In this case, if you look at the actual definition of the bridge in here, you will see that DPDK0 will exist in it, and this is basically the address for the PCI address of the NIC itself. So now this bridge can be used to send traffic by passing the Linux network stack and by passing the kernel mode altogether. But before we do that, one thing to mention is that we still have to allocate memory regions for the NIC to DMA2 or from in the user space. By default, those were given by the kernel driver in the kernel space, so we're trying to move away from that, as I mentioned. So we have to be able to allocate this in the user space. In order to do that, we have to rely on what DPDK provides us from a library perspective. DPDK provides 3 main libraries to allow you to allocate memory regions for the NIC, for DMA, as well as packet buffers and rings as well. And those are the memory pool library, basically using the RTE pool library. This is a pool of fixed size objects in memory. And those objects are normally packet buffers. So if you remember what I mentioned about SK buffer used to represent packets, this is basically a pool of many smaller objects that will represent packets. And to represent packets, it provides a different library called RTMBuff or message buffers, and it's used to represent the packets instead of SK buffer. This is far less metadata structure, so it gets better chance at being processed at a faster rate. The RTMBuff will contain both the metadata for the packet as well as the actual contents of the packet. And the last thing that exists in here is the RTE ring or lockless ring library. And this basically allows you to have access, multi-consumer, multi-producer access to the free objects within the memory pool itself. The layout of memory for DPDK looks more like that. On the bottom, you have huge pages, and those are basically either 2 megs or 1 gig, depending on the choice. And the green ones are contiguous ones, and the purple ones are contiguous as well in memory. On top of that, DPDK creates what's named as memory segments. And on top of that, there's further divisions for memory zones. So memory zones basically exist within segments. And those are the building blocks for all the objects that you create within DPDK. The responsibility for creating this layout comes back to EAL. As I mentioned, the EAL, or Environment Abstraction Layer, is responsible for the creation of all of this layout in here. On top of that, your application, or OVS in our case, will actually start creating the packet buffers for receiving and sending traffic. So you can use RTE pool for creating the packet buffers, which will have pointers to many RTE buffs within it, or message buffers. The TX and RX descriptor rings, which are still our ring-like structures, can be created in different memory zones as well. In order to instruct OVS to actually allocate this kind of memory, there is a command that comes with OVS DPDK. And as you see in here, I'm doing OVS VSCTL, and I'm setting a parameter within the switch configuration. It's called DPDK socket memory. And then I'm giving it a parameter 3072, So one clear thing about the parameter is that it actually deals with sockets. It deals with NUMA cells. So in this case, I'm asking it to provide 3072 or 3 gigs of memory on the first NUMA cell, and 3072 or 3 gigs of memory on the second NUMA cell. By default, you will only get 1024,0, which is basically 1 gig on the first NUMA cell and 0 on the second NUMA cell. This might be a problem if you have any kind of NIC attached to the second NUMA cell, because if there is no memory in it, it won't be able to copy packets in and out. So basically, using the NIC will actually fail. So now we've moved the NIC to user space. We've moved the memory structures for it to send and receive to user space. Now we have to be able to move the sending and receiving process to user space, which is basically what the kernel driver used or allowed us to do when it exists in the kernel space. And that's where the PMDs come in place. PMDs are basically pull mode drivers, and they basically run as threads within OVS. So they're regular processes within OVS that continuously send traffic out of the bridge on the physical NICs. They continuously access the RX and TX descriptors, so they're looking for new traffic. If there is new traffic, they will process it directly. And they, as I mentioned, they continuously wait for I/O. There is no interrupts in here. One thing to note here is that PMD runs within NUMA cells. As any kind of user space process, it runs within a certain processor or socket you have in your system. So NICs, as well as virtual NICs, the VNICs that you give to your KMU processes, will actually exist within NUMA cells as well. So it's always an advantage to have the PMD servicing the NIC on the same NUMA socket as the NIC itself exists. Because if you have the PMD on a different NUMA socket, you have to basically pay the price for accessing non-local memory in this case. By default, OVS will create one PMD thread per NUMA cell for each attached DPDK interface. So this means that when you have a two-socket system, you will actually have two PMDs running as threads within OVS. If you have a DPDK interface from each NUMA cell attached to OVS. So this is basically sort of a condition that will decide how many PMDs OVS by default will spin. There's always a way to change that. There is a certain parameter that you could use, PMD CPU mask, which will instruct OVS to forcibly start PMDs on different cores as well. PMDs, as I mentioned, work as threads within OVS, so they're regular user space processes. So you could easily see them using command line by using ps-TP. So I'm looking basically at the threads within the OVS vSwitchD process. And as you could see from this diagram, there is OVS vSwitchD running up here, the process ID 1775. And within it, there's two PMDs running. One of them is 1872, and second one is 1873, the PIDs for them. If I want to see exactly what cores are being used for the execution of those PMDs, I'll use task set-p-c. So in this case, I'll find that the first PMD is executed on core 0, and second PMD is executed on core 10. As I mentioned, OVS by default will start one per socket, one PMD per socket, as long as you have an interface. So in this case, I'll look at the architecture of that system, and I'm seeing that there is 20 cores and 2 NUMA cells. So this is basically the default behavior. 2 sockets, each socket has 10 cores in it. So for the first one, it started PMD on the first core in it, and for the second socket, it started PMD on the second, in the first core in it as well. So now the transmission and receive process exists in user space, the memory exists in user space, the actual NIC exists in user space. So now we have to be able to attach our VM to OVS to actually operate. So VirtIO front end is still the driver inside your VM still needs to be able to communicate with something as a back end to send the traffic to it or to hand the traffic over to it. And that's where the vhost library comes in place. Vhost library is basically allowing you to have a VirtIO backend implementation in the user space within OVS itself. And what will happen in this is that the VirtIO driver inside of your guest will hand over traffic directly to the vhost-user port within OVS itself. There's two kinds of OVS vhost-user ports. The first one is called vhost-user, and this is a deprecated kind. It still exists, but it's deprecated. It shouldn't be used in production environments. And in this case, OVS will be the server. So basically, your KMU process will connect to OVS and basically ask it to receive or send data. The trouble with that is whenever you start your OVS, all your VMs will lose connection until you actually reboot them. This basically is not very ideal in any production environment. So that's where the vhost-user client kind of port exists. It does the other way around. So basically, your KMU will act as a server. Your OVS will act as a client for it in this case. And this requires KMU 2.7+. So basically, if you have an up-to-date deployment of KMU, you should be fine from having a vhost-user client perspective. So based on those concepts, let's look at the last thing here, which is basically a DPDK-enabled Neutron OVS deployment. So once you have OVS DPDK deployed to your environment, now your VMs are connecting to it. How will they connect to it? The answer, they will look more like that. You have a virtual NIC inside of your VM, which will then connect to the host-user port within the integration bridge, and then goes to the tunneling bridge. And there is this physical bridge down there that has actually encapsulated your DPDK interface. The value of having this bridge is to be able to perform lookups against the host network stack for ARP entries and routing table, because you have to understand that DPDK is not a protocol, does not have protocols inside of it. It still has to consume the host network stack for protocols like ARP as well as routing. A physical diagram will actually look more like that. You have your guest running here, you have VirtIO driver inside of it. then it communicates back with the vhost-user port with an OVS vSwitch-D, and then the PMDs are running, continuously pulling data out and into the actual ports, and sending it out directly to the DPDK NIC. Obviously, this is a much smaller diagram than we had previously, where it had lots of tab devices, VETH pairs, Linux bridge, and so on. So this is where the achievement or performance improvement actually is achieved in this case. So in summary, DPDK tackles the traditional SDN architecture by a couple of things. First is keeping the packet processing entirely in user space. This way you don't have to pay the tax for using the kernel space for sending or receiving packets. You also have a better memory management for transmit and receive of the packet. So there's custom structs that are created specifically to provide faster performance network processing. There's also polling instead of interrupt-based I/O. So you're actually sending traffic using polling mode, which makes sure that there is no transmission and receive latency. And there's also a VirtIO backend implementation in user space, which sits inside your OVS in this case. So you don't have to go through the kernel space to actually send the traffic up and then going down again. From a performance standpoint, on a regular cloud deployment, you have MTUs 1500 on the hosts, 1450 on the actual VMs, 10 gigabit per second NIC. On regular OVS, you can achieve something between between 1 gig and 2 gig for speed and throughput as well. For OVS DPDK, you can get somewhere between 4 and 9, depending on how you tune your system. But that's basically the idea is that by default, you will get better performance of OVS DPDK because you're basically paying the tax for that by giving dedicated cores and moving away from the memory structs of the kernel for sending and receiving. So again, this becomes more of a business decision when you have a very large deployment, whether or not you want to give out this kind of cores and take them out of the general purpose computing for having better network performance for your VMs. That's basically it. Thank you very much for your time today. And if you have any questions, I'm here to answer them.
Hey, hi, thanks. Just a quick question. Once we move the NIC to the DPDK driver, we will lose the ability to TCP dump on that interface?
Yes. So there is a different kind of dumping for DPDK-enabled interface. I think they are working on a very similar to DCP dump right now, but basically, yes, you lose that.
Two questions. What's the difference between the VFIO and the BGP UIO driver?
So the VFIO driver is basically the most standardized right now for using with DPDK. I know there is a couple of other drivers such as UIO and IGB UIO as well. Those are not the default driver to use with DPDK. From a different standpoint, I'm not so sure of what exactly is the difference. Interrupts, I know at least for interrupts, are better handled with VFIO. It's more IOMMU agnostic, so basically it takes care of the isolation as well with helping of IOMMU. But I'm not sure about the difference between IGB UIO and VFIO.
Okay. And you mentioned huge pages.
Correct.
How do we calculate the number of huge pages that our application really needs?
It depends on how many packets you want to keep in memory before being processed. So that depends basically on your processing as well as the input feed that you get for the traffic as well.
Okay, and just a comment. On the newest processors, especially the Skylake, you actually have now 2 NUMAs per socket. Mm-hmm. What I'm noticing is that in terms of configuring for the socket memories, it's always the very first NUMA that's attached to the adapters. So I think by default, the EAL, you don't really need to configure it unless you have a very specialized system.
You actually, so the attachment of the NIC is not only for physical NICs. So by default, you're right, actually, that the NIC will automatically get attached to the first NUMA cell, but virtual NICs is where you will probably have trouble because virtual NICs are attached to the CPU where they get emulated upon. And that's where basically you have the socket. So if you have a VM running on second socket, its VNICs are actually existing on a second socket as well.
Okay, all right, thank you.
Yeah, no worries.
I'll take your turn because I just wanted to add a little bit to your questions. So UIO and VFIO are both drivers in the kernel. And what they're doing is they're mapping the network interface or any other driver up to user space. IGB UIO is actually the Polmo driver that is running up in user space, which is the IGB, the Intel driver, the Polmo driver that runs up in user space. And the difference between UIO and VFIO is that VFIO is actually using the IOMMU in a much better way. UIO is just creating a big hole up from kernel to user space. And then you can access pretty much anything. If you take over that region, then you can access the kernel easily. With VFIO, you have hardware that stops you from doing that.
And that's basically being IOMMU agnostic, and from this case, that VFIO actually works with IOMMU.
Exactly.
For the IGB UIO, I think there's an IXGBE driver within the PMDs itself from the source code repo, but I'm not sure about the IGB UIO itself, whether it is a special kind of UIO in this case or not.
So you're right, IXGB is for the kernel driver, IXGB is the 10 gigabit interface driver, IGB is the 1 gigabit driver, but it's a little bit confusing. The fact that you are using Polmo driver is all called IGB UIO. There's no IXGB UIO in that sense. There is IXGB in the kernel.
Okay. Thank you.
Thank you for the presentation. If we have an environment for OpenStack supported DPDK and we have VNF from vendor X, what kind of requirements on this VNF to run with supported DPDK? And the VNF itself?
Depending on how the VNF itself is set up. So basically, the first thing I would see is that you still have the VirtIO front end to connect to it. So you basically have to have a VirtIO compatible driver within the VNF itself to be able to connect to OVS DPDK level. So that's might be something. If the VNF itself is working with DPDK, then basically you're moving within the VNF from having a kernel space to having only user space processing for packets.
Thank you.
Yeah, thank you.
So we are gaining much performance, but we are losing security groups, right? We have no IP tails.
Not necessarily. So security group rules, there is an OVS driver for DPDK. So there is a project called Networking OVS DPDK.
Using flows.
Using flows
Yeah,
with OVS, yeah. So it exists right now.
It's not ready, yeah.
And it's not mainstream.
Yeah.
So that's something also, moving away from regular OVS can give you performance. So you're basically paying the price of cores, of compatibility issues, because you're operating a very different kind of deployment. Also, something I noted recently with that CentOS does not have OVS DPDK in its repos. So if you're using OVS DPDK, you basically have to build it up yourself and keep updating it. So there is always that sort of price you have to pay for that.
Okay. And what about bonding, things like that, LSCP?
I think bonding is supported, but I'm not sure. So I'll have to come back to you on that.
Okay. It is?
It is okay.
Oh, okay. Thank you.
No worries, thank you.
I think you already addressed this, but just to make sure, supposing you're dealing with a lot of different workloads, would it make sense to use this selectively in some areas and offer that as high network performance areas, or is there any kind of interdependence that you have to worry about?
No, that's actually a very good idea. That's basically what we're trying to do right now, is basically for certain kind of workloads, we provide high performance networking. For other ones, we don't provide that. And there is no technological price you have to pay. It integrates very well with the existing, as long as you're using OVS on your network nodes and the rest of the environment. It integrates very well for communication purposes. So the only thing is basically what he mentioned, the firewalls are a bit different in the way they get implemented, but it doesn't affect the rest of the network nodes. You can still communicate between VMs on an OVS, regular OVS environment, and VMs in an OVS DPDK environment flawlessly.
Is there any more information about larger MTUs and performance difference between larger MTUs on regular networks versus DPDK?
You could achieve, so over 9,000 MTU, you could easily achieve the 10 gig connection between VMs. The problem is usually about the smaller MTUs, because that's where more packets get processed. But yeah, I was able to achieve 10 gig NIC full on regular VMs.
So you're suggesting that DPDK might not be worth the effort for if you're already using large MTUs?
If you're using, well, it depends on the communication use, basically, in this case. If you're accessing large file systems, then you basically are using a large MTU anyway. So that's basically your use case. But if you have to communicate over lots of VoIP, let's say, or an FVs, so you are forced to use small MTUs. Basically, don't have that much choice.
Okay, thanks.
Yeah, thank you.
Yeah, hi. So we have some VNFs, which require like fast data path. They require SRIOV, and some VNFs require DPDK. Maybe they wanted to use the security groups and other things, right? Typically, what we do is like we create separate pools, certain hosts for SRIO and DPDK. But in some cases, like especially the edge scenarios, we run out of the compute resources. So is there a possibility to kind of mix DPDK and SRIOV on the same host?
Yeah, so this has actually been discussed a lot, maybe I think since last year, is basically running the VNFs or the VMs with DPDK inside of them and SRIOV on the host. So basically your VM or your VNF function actually itself will run using DPDK, avoiding the kernel stack of the VM or the VNF, and then using directly a virtual function of the SRIOV on the host itself. I've seen this a lot, and there is a project already out there for IOMMU, because you basically run into the same thing, that you're losing the IOMMU in your guest by doing that. So you still have to have an IOMMU on the VM to avoid them overusing each other's memory in this case. But yeah, the use case still exists out there. I think there's lots of work from companies on it, the mixing between SRIOV on the host, giving virtual functions to the VMs directly, and within the VM itself, you have DPDK running, moving your network processing from the kernel space to the user space.
Thanks.
Thank you.
As a Red Hat user, laptop 10, supported DPDK with this LIB compiled on one computer. But still, we don't see it as a production deployment. So two function as SLIB and DPDK on the same computer. So always try to build and create two profile, one for DPDK and one for SRIV.
SRIV has sort of a challenge with migrating VMs live. So this might be something that not many people would be happy with. One of the factors affecting using OVS DPDK is that basically you're using a virtual switch still. So you're not using a physical function from the NIC itself. Sorry, go ahead.
I see like with OVS DPDK, you're getting like 4 to 9 gigabits per second throughput, right? So is that using only one core per PMD, or can you increase the number of cores to get better throughput?
You can raise the number of cores, but you still have to raise the number of queues. So that's basically where you will get the tackling for the numbers in here. Basically, Virtio supports what's named as multi-queues. So you have multi-queues to communicate between the front end and the back end, and you can dedicate cores to actually process them. So that's where basically you can achieve. You can dedicate more cores, but you have to reflect that in the queues as well.
Okay, so these numbers are for 1500 bytes packets, right?
1450 on the VM itself, 1500 on the host.
So if the packet sizes go down, right? Typical iMix, say 400 bytes, you'll see a lesser throughput.
I would expect that. I haven't tested those numbers, but yeah, more packets will have to have more overhead processing. Even with DPDK itself, there's still overhead processing in it, but not at the kernel level in this case.
Thank you.
Yeah, no worries. Thank you.
Is this configuration supported by OpenStack out of the box?
Yes, there is a specific parameter in Neutron that will allow you to do that. It's not OVS DPDK is not supported. Well, I wouldn't say not supported. It's not by default in the repos for CentOS. So if you're using CentOS, you build it out yourself, and then you configure your OpenStack to actually use it. In this case.
Is there any special need or special configuration with virtual machine in Nova?
Sorry, say it again.
Any special configuration in Nova?
Yes, you still have to enable huge pages on your images. On your flavors in this case. So because you're using huge pages, you still have to use the huge pages with the VMs themselves.
Okay, thank you.
No worries.
I would like to comment a little bit more on the performance and all the discussion about OpenStack. So numbers really depend on your packet sizes, if it's iMix, if there are many different metrics when you do network performance, right? So it's really difficult for someone who has done this to tell you, well, if you had iMix, it would be like this or like that. There are quite a few studies. If you look on the internet, several people have done several type of tests with specific packet sizes and so on and so forth. I actually work for Intel. We have provided a lot of information on performance with DPDK, and we always provide the specific configuration, hardware and software configuration, because if you change something in the hardware or in the software, then your numbers will go up or down. So it's really difficult to comment just by looking at a number and say something else.
And I would say that's basically why I had the performance portion, the size, and the presentation. It's very hard to actually give numbers, because your presentation, you do this kind of study, you will have 1 gig, other person will do it, will be 2 gigs. It's very hard to, as he mentioned, that's totally right. You have to have a certain physical box, physical representation, basically, of the box itself, a number of MTU, the MTU size as well. So there's lots of factors affecting it. It's very hard to basically pinpoint and say this is going to be that or this. But that's the reason I had it this size in the presentation, because it's very hard to mention that.
Plus, you have to bootstrap your platform the right way, CPU pinning, and so on and so forth. And actually, there was, since we are in OpenStack Summit, there was another presentation from, I want to say NTT, I'm not sure, who have done a lot of performance analysis with OpenStack, and they have come up with some blueprints on how you can provide configurations through the flavors so you can maximize your numbers. In my opinion, there is quite a bit of work to be done for DPDK to really run efficiently under OpenStack, and OVS also is dropping the performance because it's doing packet processing. But I think we're going towards the right direction, and we need to enable all these details in the OpenStack context. Thank you.
Quick question. So those figures are for which packet size?
1450 MTU for the VMs.
Oh, okay. Thank you.
Yeah.
So, quick question. How many cores you dedicated for the host, the DPDK host?
On those tests or just in general?
In general, like if you take a 20 core, for example.
So by default, it creates 1 per NUMA cell. So if we're judging based on 1 NUMA cell per socket, so in this case, you will dedicate 1, let's say, for 16 cores. So I would say on average, maybe 1 per 15. So you have 2 on your host out of the 32 cores in this case.
So you dedicated 1 course?
That's the minimum you can dedicate, because if you don't have a PMD on the same NUMA cell, you basically pay very much price for that, because it's different.
Yeah, someone asked the question on the bonding, like for example, you have NICs on 2 different NUMA. Do you typically what we do is for NIC diversity, we take ports from each of the NUMA, but for DPDK, there is a hit in that, right? If you're cross NUMA, and if your VMs are in, it has to be on a single NUMA.
With any kind of different NUMA cells, you basically have to pay the price for accessing foreign memory in this case, or non-local memory.
So this is a general practice, they always take a bond across different NUMA? I'm just
I'm not, I wouldn't be sure to say that for this question, but I would say in a general concept, that if you have to cross a certain NUMA cell to access memory, then basically you have to pay a price for asking for it.
Okay, thanks.
No worries.
Hi, I have 2 questions. One about the emulator pin. Does it have any meaning when using the DPDK?
Sorry, say it again.
The emulator pin of the libvirt.
Oh, okay.
Since we're using the vhost-net, does it have any meaning? Does it still being used when using DPDK?
I'm not so familiar with it, so I'll probably be speculating if I answer that, so I wouldn't do that.
Okay, thanks for being honest. And the second question is regarding the Linux bridge you explained that is involved. We have installed the OVS DPDK over OpenStack Neutron, and by default it didn't create the brton and the brtap, and I don't see the meaning of it. Why do we need it if the VNF has routing capabilities? Can you please elaborate more about it?
So you're saying when you deployed for OpenStack Newton, it didn't create the tunneling and the integration bridges?
Exactly.
Okay. But how did it connect to the actual network?
it created a vhost port in the OVS database.
So this seems more of like a custom deployment for OpenStack in this case. It's not a traditional one, or is it?
Traditional, as far as I can tell.
Yeah, I wouldn't be able to answer that as well.
What is the use of the Linux bridge? Don't you lose some performance when you set the
Linux
traffic?
bridge you have in here is not related to OVS. So the Linux bridge, because I think there's confusion on Linux bridge versus the BR. BR int is not a Linux bridge. It's actually an OVS switch itself. OVS, so BR int and BR tunnel, those are actually not Linux bridges. They're OVS switches in this case. Linux bridge is a different technology. It's very old and it sits in the kernel space. So basically that's why it doesn't fit here, because you can't move it to the user space, or no one has tried at least.
Okay,
So.
okay. Thank you.
But yeah, when you look at the integration and tunneling bridges, they're actually not bridges. They're actually, let me show you maybe. Oh, sorry. Kind of sad. So the integration and tunneling bridges, the name itself is BR something, but they're actually switches within OpenVSwitch. Okay, thank you very much for your time today, and hope you have a good evening.